as well. So now, so far, we looked at convolution in the nodal space. We call that a nodal space or a spatial domain, a nodal domain, meaning that we're looking at each node and we are looking at the neighbors of the node and we are defining that as a function of the adjacency matrix. So everything in the nodal domain. Now, another approach for that is to use the ideas that we discussed earlier in this lecture and define these in the Fourier domain, or in graphs we call that a spectral domain. So now for that we need to define what a graph spectral domain is. What is a Fourier transform on graphs, right? So we don't have any of those for graphs naturally. And the building block of essentially many tools in signal processing is the Fourier transform. So if you define what Fourier transform is on graphs, you can use that and apply many signal processing operations or redefine many signal processing operations starting from those building blocks. So just a reminder, earlier in the lecture, we looked at the Fourier transform. And we said that Fourier transform is expansion into Fourier bases, where Fourier bases are defined using these exponentials here. So now what we want to do is to see what are these, and then how we can redefine, find analogs of these bases in the graph domain. So these are essentially, so let's look at Laplace operator in the basically time domain. I can write this as the divergence of the gradient of function f over time domain. Now, I can see that if I write this out, this is essentially the eigenvalue decomposition because of these two are the same, right? So I can essentially say that and you can see that we have recovered here the exponential basis that we use for Fourier transform. So essentially, the exponential basis of the Fourier transform are the eigenvectors, or because this is an operator, we call that eigenfunctions of the Laplace operator. So now the idea is clear. We have a Laplace operator, we find its eigen decomposition, we select eigenfunctions or eigenvectors of this operator as the basis for our Fourier domain. So what should we do for the graph space now? I'm asking you guys.
Fourier transform to the coordinates? No.
Now, how to redefine Fourier bases in the graph space? It goes back to the session that we discussed about clustering. And we showed that Laplacian matrix of the graph. Go ahead.
The eigenvalue or something. Yeah, the whole work.
Those are related, yes, but it's simpler than that. So the idea is that Laplacian matrix of the graph is analog to the Laplace operator in the time domain. So what we can do now is that since the basis for the Fourier transform in this continuous time domain are the exponential eigenfunctions of this Laplace operator, what we can do is that take our Laplacian, show its eigen decomposition, and those eigenvectors now of the Laplacian matrix are basis for our Fourier transform. So, and that's the idea, and that's why the reason we cared about eigenvalues in general in the clustering, and we will see one example later here. So now we have these eigenvalues. So we said that this eigenvector is representing the basis for our Fourier transform, and these eigenvalues are representing a notion of frequency. What that means is that if my basically, if this is a small, the corresponding basis is oscillating slowly. If this S is higher, the corresponding component, corresponding eigenvector, is oscillating more rapidly, right? So that's what that basically is basically how it carries a notion of frequency. And that's what we are going to use later to define this notion for graphs as well. So now we say that Laplacian matrix is an analog for Laplace operator. If anyone wants to go back, I think it was in lecture 5. So we can use this to redefine Fourier basis on the graph domain. So for that, we say that Laplacian matrix is a positive semi-definite matrix. So it has a set of eigenvectors that are orthonormal. I'm showing the set with vectors UL from L from 0 to n-1 for a graph that has n nodes. And then it has a set of real non-negative eigenvalues that I represent here. So now what happens is that these are eigenvalues and eigenvectors of my Laplacian matrix, and I'm going to use them to define the basis. So in the matrix form, I can write, so we're usually applying operations in the matrix form. So in the matrix form, I can write this matrix decomposition, eigenvalue decomposition in the quadratic form. And then this U is matrix of eigenvectors, meaning that every column of this contains my eigenvectors of the Laplacian, and then this guy over here, matrix lambda, is a diagonal matrix, and every element on the diagonal of this matrix is an eigenvalue of my Laplacian. And basically these are eigenvalues corresponding to the associated with the corresponding eigenvector. So the element 1, 1 is associated with the first vector, first column of the matrix U, and so on and so forth, right? So, and the set of these eigenvalues, we call them the spectrum of the graph. And then we can show that, or we have shown that previously in this class, that for a connected graph, the smallest one is 0. I mean, for any graph, the smallest one is 0. For a connected graph, the multiplicity of the smallest eigenvalue, 0, is 1, meaning that we only have one eigenvalue equal to 0. If it has two components, we have two eigenvalues equal to 0, and so on and so forth. So lambda max here is our maximum essentially eigenvalue, our largest eigenvalue. And we're assuming that we have sorted these eigenvalues so that we looking at their index, we know which one is larger than the other one. So when we say lambda n minus 1, we always mean that this is either equal to or larger than any lower index lambdas. Now, we want to use this in our favor to define Fourier transform. So when I'm basically transforming some signal into Fourier domain on the graphs, what we are doing is essentially multiplying with this eigenvector matrix. So that way, I'm projecting these signals onto each basically eigenvector. I'm projecting this signal onto different bases, and I'm getting a notion of essentially Fourier coefficients in the graph domain. So mathematically put, we can write this as essentially the eigenvalue, the coefficient for your coefficient of f is equal to projection of f onto this eigenvector ul, and then this is just a sum of different projections of different elements of that function f. So in the matrix form, we can write this as ut times f, and similarly, we can use eigenvectors to transform this back into the nodal domain. So we reformulate, we basically write this in the matrix format as we have a vector f hat, which contains coefficients of my Fourier transform, and I'm multiplying that to the eigenvector matrix. This time no transpose. We are essentially summing different basically contributions of these basically different eigenvectors, so that we construct what the value at each index of f is. So, and you can see that in the essentially index notation about that. Now, what's interesting is that, and what's very important to make sure that our analogy is correct, our analogy that we have used the essentially eigenvectors of the Laplacian matrix in order to define Fourier basis is correct, is to see if the same notion of frequency exists using this analogy on graphs as well. So what that means is that we want for the eigenvalues that are lower, we want the eigenvector to be smooth. For the eigenvalues that are higher, we want these eigenvectors to change more rapidly, right? So same idea that we had in the Fourier domain, right? For the smaller s's there, we wanted to have the corresponding essentially exponential function component to be oscillating slowly, and then we wanted for larger s's our basis, our component to our basically exponential component, which was our Fourier basis for that s to be oscillating faster. So here, if we use Laplacian matrix and we decompose that, and that's what these eigenvectors and eigenvalues representing, we will see that for eigenvalue equal to 0, we will have a corresponding eigenvector, which is a constant value, and that constant value is 1 over square root of n for every element in that vector. So that means that it is essentially constant, right? You want it not change too much, and that's what you get, right? Then for smaller basically values of lambda, which are close to 0, you want this to slowly start to vary, start to oscillate. And this oscillation across the graph means that how the values change from one node to the other, right? So the first eigenvector had all elements the same. When I find the element corresponding to each node, it is the same value. Now, and you will see that in basically in a second, just in a couple of slides. But the idea is that if you have this function, this should not be u0 in the second line, ul, right? So the eigenvector ul associated with eigenvalue lambda l should change slowly from one node to the other node. And that means that, for instance, let's say that you have a graph of social interactions of different high schoolers in the world. And for example, the people, the basically high schooler who are in New York have a set of interests that are close to each other. They follow the same, essentially, pop star. They all now listen to Harry Styles, probably. Now, if we move to Sweden, those people are essentially probably have a more set of, interests that are close to each other, but very different from the ones in New York. So the nodes that are close to each other have similar interests. So let's say that they listen to AHA. And these people in New York listen to a different singer. But still, the ones that are close to each other are similar to each other. So that means that's essentially a smooth function. It is varying slowly across the graph. Now, for eigenvector UL again, that is associated with higher eigenvalues, these eigenvectors should vary more rapidly from one node to the other node across the graph. Now let's look at an example to visualize what all that means. So let's say that this is a graph that is constructed of few components. A few nodes. Here is 50. And now what we want to do, we want to visualize these eigenvectors of the Laplacian matrix over this. So I perform an eigendecomposition of the Laplacian matrix of this matrix. And what I get is some vector. I get that vector and I get some eigenvalue. So I get a matrix of eigenvectors, right? And then for each of those columns on that matrix, I have an associated eigenvalue. For the smallest one, it is going to be 0, lambda 0 is equal to 0, right? And we said that it is a constant across the graph. So I have an n-dimensional eigenvector, and each element is corresponding to one of the nodes in my graph. And that value is the same across the graph because it's a constant vector. Then I'm using lambda 1 as a basically way to visualize this graph. And I see that for lambda 1, this is a smooth function that varies for the similar nodes that are basically the nodes that are connected to each other. It varies slower. So nodes that are connected to each other have similar values corresponding to elements of the eigenvector. And when I move to the essentially the ones that are farther from them, those are similar to each other, not same, similar to each other, and it varies slower across those nodes. But when you move from one side of the graph to the other, you see that the changes are more, basically, the values are more different. Now, this is very close to the reason why in clustering, we were using eigenvector matrix as a way to cluster, because they basically, and to essentially identify different nodes. So, and you can see that using this second smallest eigenvector, I was able to cluster this network into two basically clusters that are closer to each other. There are more edges in between the nodes that are in each cluster, and those clusters, you can see them intuitively using different colors, and kind of you can sense that. And this eigenvector corresponding to the second smallest eigenvalue is called Fiedler vector. It is very important vector. It has many uses in different applications in spectral graph domains. Lastly, I'm going to show you the eigenvector corresponding to the largest lambda, largest eigenvalue. And then you will see that this is more rapid changes are observed across the nodes that are neighbor with each other on this node. And I'm assuming that part of the reason that there are less changes here is because I have I have set some basically lower and higher limits for the coloring. Probably they're all higher than that, but they're still different. So that might be part of the reason. So it's 444. We have a few slides left, but we can continue that on next session. So remember, for next session, you're gonna do a PyTorch session. If anyone wants to follow here in class, just make sure you have some basically PyTorch installed, and every package you need to essentially run the homework. Okay, I will see you guys on Thursday.
Can I ask a question?
Go ahead.
So the color here means some kind of similarity measure. Is this the magnitude of the eigenvector? What's the color?
I'm gonna show this to you. So this is basically a vector, a graph that has 3 nodes, right?
Yeah.
So for this, what I define is a 3x3 adjacency matrix, right? And I will have a 3x3 Laplacian matrix as well, right? So if I decompose that, I will decompose it to 2 things, a U and right? So each of these vectors, U1, U2, U3, is representing one eigenvector corresponding to the Laplacian matrix of this graph, and these elements, lambda1, lambda2, lambda3, and everything else is 0, right? So for this graph, I have selected this guy, and I'm assuming that these are sorted. So but just sorting them means that sorting these vectors as well. So it's basically no problem. So let's say that this one is 0. If I select this, these are all 1/n. So now I select this. This element is corresponding node 1, corresponding node 2, node 3, right? So what I have done is that I have selected this value to visualize node V1. So that's what you see there. So each color that you see, it's just a color plot for different values on each eigenvector.
So each node has its own eigenvector.
No, each node has an element corresponding to it on each eigenvector. You have one eigenvector U1. Each element is corresponding to one node. You have a U2. Each element is corresponding to one node. You have U3. Each element on U3 corresponds to one node. And that's how we define essentially these transformations from and to Fourier space or spectral domain, graph spectral domain.
That makes sense. Thank you.
Sure. Any question from our online audience? All right, so I will, if you have any questions, just let me know via office hour. If someone wants to come in person, that's fine too. I will probably be 5 minutes late until I get there, but I will see you guys then.